is the mathematician's paperweight problem. This is the only example I'm going to do for 8.3. You're going to do at least set up area formulas for a bunch of different shapes. But the idea with this is that you can create a three-dimensional shape by taking a two-dimensional area formula and creating a bunch of little cross sections that come up out of the picture. So in here it says a mathematician has a paperweight made so that its base is the shape of the region between the x-axis, here's the x-axis right here, and the curve y equals 2 sine of x. So here is the region right here. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. What that looks like is this. I've just drawn the diameter of the semicircle, and it's going to come up out of the page at us, like that. And then if I did another one, and then it would come up out of the page, like that, and then another one, and then up out of the page. Okay, so what we have is a bunch of half circles stacked right next to each other from left to right, creating a three-dimensional object, and that's my mathematician's paperweight. So as those come up out of the page at us, and of course they're as close together as can be, it creates this, once again you got to fill in the model here, that mathematician's paperweight. Now here's the deal. You can create any shape you want. You could have triangles coming up out of the page at you. You could have full circles coming through the page. So you'd see the half circle above and then half circle below. You could have squares coming up out of the page at you. You could have trapezoids. I mean, any shape you want to make can be done by this method. And all it amounts to is integrating from left to right, from A to B. Here's A over here. Here's B over here, whatever the cross-sectional area is. And in this case, the cross-sectional area is 1/2 pi r squared, because that is half of a circle. So any questions so far? All right. So the only thing we need to figure out here before we can integrate this is what A and B are. Obviously A is 0 in this case, right? So we need to figure out what B is. Any ideas on how to figure out what B is? Equals 0. If I want to find B, yes, solve for x in which equation? Yeah, y equals 2 sin x. So we have 0. That's so much. So we have 0 equals 2 sine x. So can you solve that for x? It's 0 equals sine of x. So where is sine of x equal to 0 besides 0? Yes, pi is the other place. So we're going to go from 0 to pi here. Okay, so my integral for finding the volume goes from 0 to pi, and I'm going to integrate the area formula here. So I'm just going to integrate 1/2 pi. Now I'm going to replace r squared with the ever-changing radius represented by the function 2 sine of x. There it is. And you can go ahead and do that on your calculator. So why don't you take a minute to do that on your calculator. So we get a volume, just plug it into your calculator, of about 9.869. And the units on this, I think I might have done inches. Did I put units on there anywhere? Does it say cubic units? So that's it. So the only thing that'll change is what the area formula is. Okay, it could be any area formula you've seen from geometry. The ones that you're going to see in today's lesson are triangles, rectangles, different kinds of triangles. A right triangle with its base in the shape here, or it could be an equilateral triangle with its base in the shape. That would kind of be more of a pyramid-looking thing coming up. Or it could be a full circle, which would go right through the page. And I think that's about it. So rectangle, two different types of triangles, full circle, half circle. So that's it.